All right, so in this lesson we are going to look at the graph, or if we're going to explore the different details about the graph of an exponential function. And so this lesson, this lecture here is intended to be as a continuation, from what we've learned earlier about the details about the introduction of what an exponential function is. So here it is to be a continuation. So it is extremely important that you must watch this lecture here after you have seen my earlier lecture where I introduced about the exponential function. Okay, and the reason I have this here as a separate lecture here is simply because I just want that this particular lecture here has its own details, has its own specialty, and so for that reason, to keep the lecture from being too lengthy, to keep one lecture from being too lengthy, then I record this. I record this lecture here as one particular separate lecture so that I can restart the example numbers like that. All right. Okay, but other than that, let's get into it. All right, so let me briefly remind anyone viewing the video lesson here about what we have done a little bit, just only a little bit, from the introduction of exponential function that I brought in earlier. So in the earlier the lecture where I introduced about the exponential function, I brought up that function f of x equals 2 to the x, and I showed that process there, and that was the only one problem where I showed the process of sketching the graph. And so we have seen any viewer arriving at this lesson here must have, after you have seen my earlier lesson about how I introduced the exponential function, then you have seen how I show if we were doing a hand sketch version of the graph for this first exponential function 2 to the x, then that exact same idea is going to be used here again. So right now, to start, I am going to start out with one particular example where I would like to just repeat those steps, but this time I am going to speed up the process a little bit, okay? But I want to briefly reveal how we can just think about if you were one of those first generation mathematicians or math people who came up, who were discovering the graph of an exponential function, then this is the kind of steps that you were doing. And think about those historically, back at those times where computers were not around, calculators or graphing calculators were not around, and this was the way how we got it done. All right, and so we have seen 2 to the x function being graphed earlier, so there's no need to repeat that one. Let's repeat the steps, but now we want to, how about I'm going to call it example 1, but we want to say we're going to sketch the graph. It means now we try to do this by hand with paper and pencil, if we could, okay? Sketch the graph of, so now I'm going to give, how about in part A of the example here, how about the function 3 to the x. So f of x is 3 to the x. So now I just made that call right there. Okay, so the standard steps here is to get the table of values. Just think about if we are, and I mentioned about being the first generation of mathematicians who were to explore or to discover the graph of an exponential function. And think about, historically speaking, think about if we were learning, then if this was a completely brand new function compared to the other functions we have learned. Okay, if this is a completely brand new and we have to discover the graph from scratch, then building a table of values is always the first step like that. Okay, so I'm gonna assume that the function setup is easy enough so that anyone can easily get the calculated value. Let's just start right into the steps where we got the table of values constructed. All right, so with the table of values, x for one column for x, the input, and one column for the y value, which is the output of our function, 3 to the x. So our function here, the rule of this function is 3 to the x. All right, so I'm going to sketch down a few values. Now, and so think about how it works here, but if we are the first time exploring the graph of an exponential function like this, then it makes natural sense that we start out with a value like x equals 0, because we want to, naturally speaking, we want to find out if the function can take 0, can take a positive, and can take a negative, so that, as as long as, I mean, along the way that we are exploring the graph, we can also making some conclusion about the domain of that function we're working with. And so generally here it's an exponential. It's a base 3 to the x right here. So I start out with x equals 0 for input. And so needless to say, x equals 0 give me output value 1 right there, because 3 to the 0 value is 1. Now when input is equal 1, when x equals 1, we're looking at 3, because 3 to the first power is 3. And like I said, allow me to be the skippy on this step right here, because I'm assuming it's simple enough that anyone watching a video can and you can always pause along the way and double check with my output value calculation right there. All right, so 2, when input x equals 2, so 3 squared, 3, the rule says we raise the base 3 to that power being the input. And so now it's going to be 9, one more input. So these are the positive inputs that I'm getting into. First, I started out with x equals 0, and I got 1, and then these are the positive inputs. So 3 equals, now when x equals 3, then 3 to the third power, base 3 to the power 3 is going to be a 27. And you can always double check my calculation on that. All right, and I feel it should be enough for all of the positive numbers inputs. Yeah. And yes, you can also use a 1.5 or 2.3 or something like that in between these values, but there you need the assistance of a calculator. So here, think about without a calculator, we stay with whole values to keep things simple. That's all. All right, so now when x equals -1 for the inputs, and I now purposely put this in a certain arranged way right there of the input x values. So when x equals -1, our outputs turn out to be a 1/3. All right, because this is the same as 3 to the -1. Okay, that's how we substitute -1 into the function, and then we get 3 to the -1. But really, that's final output is a 1/3 or 0.3333, and then a lot of 3 right there. But I prefer writing this in fraction. Okay, and so in that way, when x equals -2, let's try a little further into the negative values here. So x equals -2, we're looking at 1/9 right here for the output. And this is simply because we're looking at 3 to the -2 power. And you can always double check with me on that. You can use your calculator, okay, and then double check and verify that these two are the same value. Okay, and then when it gets to something like this, I just want to, personally, I just want to completely leave the decimal values out. I only want to stay in exact expression being in fraction like this. Okay, so this is the output. So we have a pair of values, -2, 1/9. And then let's try one more negative input. How about -3 right here? Now I'm looking at the output being 1/27. And this comes out because we're looking at, when x equals 3, we're looking at 3 to the -3 power. All right, so that should be enough for our table values. We can continue going further into the negative, but I feel there's no use for doing that. Okay, and then we can also use the values between these whole values here, but that requires the assistance from a calculator, and I don't have one right now. Okay, but you can always try. All right, so now let's quickly, once we've had our table values here constructed, let's quickly turn over to the graphing space right here. And I'm using a software program, a graphing utility, but really, when you're watching this, pretend that if you're using a piece of graphing paper with your axes already ready and with numbers and grids already ready for that. And then it's just about how we bring this table values as plotted points on the graph, and then we're gonna draw the picture of the graph through. That's all there is. All right. All right, so now on my empty graphing space with my Desmos, the graphing utility right here. So the table of value we have seen on the board earlier gave me the following plotted points right here. All right, so right here with this very first one on the table, I chose 0 for x, 1 for y. Okay, and then the next point is here, 1 for x, 3 for y. And this is the next point right here that I chose on the table. 2 for x, 9 for y. Right, so these point comes out just reflecting what was on the table. Now we put them as plotted points on the graph, where we put the grids on, and again, x value is the horizontal coordinates and y value is the vertical coordinates. And now this point right here is when x equals, this point right here reflects that pair of values, negative 1 comma 0.333. So 0.333 right here is in Desmos. With the graphing utility I'm using right here, it can only show in decimal, but really this is 1/3 right here. So this point is equivalent to that pair of value negative 1 for x and comma 1/3 value for y right here. That's the point. And then here we're looking at that point negative 2 comma 0.11111. And this is the value for 1/9 right here in decimal, okay? And that's this point right there. All right, and the last point here is needless to say, it's negative 3 comma. Now, so in decimal is 0.037. This is really 0.0366666 right there, but that means it's a 1/27. Okay, so these are the points. And so now even before, let me clear the labels of the axis, the label of the points away. But now after I put the labels away, we already notice that from the left to the right, the points here form into a curved shape, and that curved shape is very similar to that 2 to the x we have seen back in our earlier lecture when I was introducing about the exponential function. So the way how it is, these points are rising, they're all rising. These points forming to a path that's rising from the left to the right. But the amount of rise, it's rising slowly for those points to the left of the y-axis. And then those points are starting with this point right here on the y-axis. Those points to the right-hand side of the y-axis rise a lot faster in a much more rapid way right here. All right, and so now when it gets into graphing it, then it makes sense that with paper and pencil, here's how if this is our graphing paper, then we're going to graph. To make it easy for myself, I would graph from that point right here, and I'm going to continue sketching a curve. How nicely can we make the curve? That's not important anymore. Okay, as long as our curve is going through in a curvy way and not a straight path connecting through these points, that should be good enough. Okay, and now from this point, I'm going to draw the other part that's going through these points right there as another part of the curve. All right, and so that's the shape of the graph that we are drawing right there. All right, so that's how we make the sketch, and it should be that simple and that easy right there. Of course, I spent in some time explaining some of the steps right there, so it took some time. But when it gets to this graphing an exponential function using completely paper and pencil and with table value started out, it shouldn't be that hard at all. And the point here is that eventually we only know that this method always exists for anytime we're exploring the graph of a new function. But in the end, the aim for this lecture here is that eventually we're going to migrate over using technology to handle the graph here so that we can pull up many graphs at once, many graphs from many exponential functions at once, so that we can start recognizing even better properties about a graph right there, instead of just staying with table of values to spend so much time on constructing one graph. Yeah. All right, so for viewers to practice, let's try simply try one more problem right here. So I'm going to call that part B. All right, so we're still sketching the graph, but let's look at a different graph. And for this one over here, I'm still leading the steps, but I want viewers or students of mine to try this as independently as you can. So try this as an FYT as well, okay, for your own trying. So how about we're going to sketch the function f of x equals, so we have the base here being a 1/2. So positive base, positive number, and then being the 1/2 here. So I'm going to raise that base to the x power. So it's entirely an exponential function. Okay, so let's get the table of values. And I'm even going to move a little faster compared to how I was doing that with the earlier one right there. All right. So as far as table values, let's look at x equals 0. Okay, I'm starting out with x equals 0, and then so x equals 0, 1/2 to the 0 power is 1. Anything non-zero raised to the 0 power is 1. Okay, so that point is easy. The next one here, when x equals 1, So we're looking at 1/2 raised to the first power, which is 1/2 again. All right, and then when x equals 2, we're looking at 1/4, and you can double check with my calculation here. This simply came out because we're looking at a 1/2 square, and you can use that for your own calculation purpose. Right, and then when x equals 3, we're looking at 1/8. All right, and 1/8 came out because we're looking at 1/2 raised to the third power. Okay, and then now I can plug in a negative number for x. So let's say -1. Our value will come out being 2. All right, and that's simply because we're looking at 1/2 but raised to a -1 power. You can use your calculator to double check with this. All right, and then -2 is going to give me output 4. Okay, and that came out because we're looking at 1/2 raised to a -2 power. So 1/2 raised to a -2 equals 4. And you can always double check my calculation with any of this. Okay, and then when x equals -3, we have outputs being +8, which is now a 1/2, the same as a 1/2 raised to the -3rd power. All right, so that's the table of values. I showed the calculation step quickly, and then these are the outputs, the final outputs value that together with the x values correspondingly. These are the pairs of coordinate points right there. All right, and so we're going to use these pairs of values to make the plot points, the plotted points. All right. All right, so one more time back on my empty graphing space with Desmos, my graphing utility. All right, so this is the plotted point. This is the set of plotted points from that came right out from my table of values right here. All right, so this time again from the left to the right, that's the one general convention that anytime we're looking at the graph. So from the left to the right, these points here form into a shape, and it's going one way similar to the earlier graph that we have plotted. So for right now, just we don't want to think too far we don't want to think of any details that are too far away from our understanding yet, but just think about these are the plotted points that right out from the table values. So this point, for example, is corresponding to that point, to that pair of values, -3 for x and +8 for y. And this point is corresponding to -2 for x and +4 for y. Okay, and then the grids are telling the true story. And then this is -1, 2. This point is 0, 1. This point here is 1, 0.5. So 0.5 is a 1/2 from our table of values. And then we're looking at this next point is a 2, 0.25. So 0.25 is the decimal value of 1/4. And this is 3, 0.125. So 0.125 is the decimal value of 1/8. So these points come straight out from our table of value that was table of values here that was constructed here on the board. All right, and so one more time, I'm going to get back to the graphing space in full screen. And so now let's put in the graph. So from the left to the right, right here, we're going to start making the sketch of the graph. All right, so I'm going to draw the right piece first. All right, and then I'm going to draw that back piece right here, the piece of the graph that's on the left-hand side of the y-axis right here. That's why I call it the back piece right here. Okay, so this is the shape of our function. This is the graph of our function 1/2 to the x. All right, so as far as getting the graph sketched, that's how it is. So think about the empty graphing space I was using. That was your graphing paper. So we have a table of values, and we put the table of values as plotted points on the grid, and then we draw the curve through. And then whatever the shape that's where we're gonna start putting as many graphs as possible. Okay, so that we can start recognizing a generality about the shapes, the shape of these graphs. Yeah. All right. So in this example one, we've had about 2 problems where we're sketching it by hand. But again, the intention of this course is not to emphasize on how we sketch these graphs by hands. But now from this point on, we're going to start letting technology assist our work right here by quickly getting the graphs done on any of these functions. Okay, so now let's call it example 2. But my aim of example 2 is to show you how you can use the technology. So we're still going to try to get the graph of a given exponential function, but we are doing that using the technology, okay, using a graphing utility. I personally use, and I use a lot with the Desmos graphing utility simply because it has all that flexibilities, but that does not limit you to only use the tool I use here. If your instructor is asking you if the syllabus of your course is requiring you to use the TI graphing calculator, use the TI graphing calculator. If your professor requires you to use the HP graphing calculator, use the HP graphing calculator. Okay, I'm pretty sure it has a similar graphing feature here. In this example, I'm going to show how to run with Desmos for my own students if they are learning from me. And then I also show how to use the TI calculators, the newer version and some of the older versions as well. But then if you're running anything else, any other graphing utility aside from these, you can just spend a little time, read the instruction manual of any of those before you use them. That's all. Okay. All right. So now I'm going to say in example 2 here, we want to graph. Okay. So we want to get a graph of the given function, okay, and then using some kind of technology. So let's look at how about part A right here. Our function f of x equals 3/2 raised to the x. Okay, so we want to graph the function there, that given function, using a graphing utility. All right, so here I mean some kind of technology right here. All right, so this is part A right there. We want to graph, and so if I have another part B for this problem, it means the exact same thing. We graph the given function using a graphing utility. So my plan here is, in this same example, I am going to show you how to use how to get the graph of this function here of any of the given function here using both graphing utilities, the Desmos. Okay, so for this lecture right here, particularly, I am going to aim at Desmos for anyone using Desmos, planning to use Desmos, and I'm going to be also showing how to use that on the TI-83 or 84. Okay, so those are the two graphing utilities that I'm showing in this particular lecture over here, this video. And then if you're using something else, I'm sure, again, like I said earlier, I'm sure there will be similar functionality compared to these. Okay, but you have to spend your own time a little bit reading the instruction manual. All right, so first with Desmos, all you do is go to www.desmos.com. The name of the program is here, Desmos, so desmos.com, and then you will be able to be directed to the website that has this particular program right here. All right, so now when you're in Desmos, suppose all right, so this is the graphing space with Desmos right here, and suppose you already knew how to get to Desmos, and so here on this left hand side panel, and this is our graphing space area. So on the left hand side table over here, we want to give that for any machines, for any technology, we have to give what that function is. We have to provide the technology. We have to let the technology know which function we're graphing. So here, now ideally, ideally, or for simply speaking, you can just type in parentheses 3/2, okay, and then close the parentheses. Use the right arrow to get back to the normal mode right here. And close the parentheses and raise power by the hat key, raise power X. Just typing it out like that. Desmos has already popped out that function for us, the graph of a function. So simply speaking, that's how we get it done. Okay, simply speaking, with Desmos, that's how easy it is. Just pick a command entry line right there, type in the number, the function, the rule of the function, in terms of X, in terms of Y, in terms of whatever. Okay, and then it pops out immediately the graph. All right, but then for some extra learning with Desmos, okay, then I highly recommend doing this. So I highly recommend to also type out the function as following: f of x equals Okay, so f of x equals, so now doing this is still gonna graph, the Desmos is still going to give you the graph of the function 3/2 to the x. But it's also, but here Desmos also will also store our function f of x in case we want to do some calculation later on. So for example, once we type a command like that, Desmos will know how we define f of x. So that in case we have to do f of 1, for example, Desmos will know to evaluate this function at x equals 1 and come out with the output value for us. Okay, so that's some advantage of doing this. Otherwise, without doing that, if we had this command entry line without the functional notation f of x equals, then in any of the command entry following, then Desmos will not know what to do with f of 1. All right. And so now this is the graph of Desmos. So that's how easy it is to get that. So if you want to change to a different graph using Desmos, just go, you can either clear that out, completely delete that out, or hide the graph away by click on that graph icon. And if you want to create a new function, okay, then we can go the 2 to the x, for example. And so we pick a separate command entry line right here, 2 to the x. And then the graph is even colored in a different color, and you can also change the color of the graph by hold for a couple seconds. It's gonna pop out. Click on the graph icon right here and hold for a couple seconds. It's gonna pop out a menu for you to change the different colors of your graph, and also is it gonna be solid line or dotted line or fine dotted line like that. Okay, so now that's not important right now. Okay, so let's get back to our f of x equals 3/2 to the x. That's the one for our problem like that. Okay, so now if you're unhappy, if you're not feeling satisfied with the default grid setting, you can go to that, click on that icon right here, okay, and then we can set the step right here so that the grid will always show a step of 1. So 1 and 1, so this is step 1 on the x-axis. This is also step 1 on the y-axis. So now the vertical axis are showing scales going in steps of 1 in step. And then also the horizontal scale going in steps 1. Now, I personally don't like all of these minor grids right here. And so in that setting right there, I'm going to turn those minor grids off. Minor grids line off. So now it only shows the major grid lines right there. Now, I personally like to show the arrow pointing one way, pointing up on the y-axis and pointing to the right on the x-axis. I'm going to select arrow to turn on displaying arrows. And then my style that I prefer, I use this one. Okay, all right, and then if you want heavier line weight right here, then we can select that option, and then it will make the heavier line weight easier for our visualization. It assists our visualization. So that's how we quickly get the graph of a function, any function. And here I'm using Desmos to get the graph of our function 3/2 x, 3/2 to the x. Okay, using Desmos.com like that, using that graphing utility with Desmos. All right, so now with the graphing calculator on standard, I used a TI-83 or 84 calculator. The version I'm using here is even advanced, is the latest version, so it may even look a little bit more advanced than the version you're using. But it should, but really all the functionalities will remain the same. It's just the look is a little bit more upgraded. Okay, so in order to graph the function 3/2 to the x, here's how we can do it. We can click on that button, y equal, okay, and then the newest version that I'm using here, the newest version of the TI calculator I'm using here, has all the color coding, has a lot of color codings for our graphs, and it can take up to 9 different graphs right here. So it's our first one on this list right here. So let's go ahead and type it in. Now, parentheses, 3/2. Okay, close the parentheses, and now we want to raise to power And this is the part where I was saying something about the newest version versus the older version right here. With this newest version, when we put the hat key, so hat key is always the hat key is almost in these days the international convention for raising power. It's the same with Desmos. So when you in Desmos, if you want to raise to power, we use a hat key. So it's the same with the TI calculator here. But now for this advanced version, advanced software, the Plus CE software, when you raise power, it's also gonna put your cursor in superscript mode, whereas the older version doesn't. The older version doesn't put yourself in superscript mode. And later I will quickly swing over to the older version so that we will understand what I'm talking about. Okay. So this is the TI-84, but the latest software, the Plus CE version. So 3/2 in parentheses. Now I'm ready to type X. So the X is the variable, so we have to use this variable button instead of the usual numerical X that can be found right here. That's not the one. The one we want to use is right here. So just click on that X. And now for users who really are using this advanced software, the most advanced software of the 84 Plus, I highly recommend you to follow the following habits. To do the following habits. Anytime you are finished with the superscript mode, exit out of superscript mode by clicking on the right arrow key that brings your cursors back to the normal mode. Okay. So the older calculators don't have to worry about this, but for the users who use this advanced, most latest operating system of the TI-84, then make sure you exit out of superscript mode to prevent some confusions of the later problems. All right, and so now that's how we enter. We have now finished entering the function, and so now our function is expected to be in blue. Now we click on the graph button. No need to hit save or whatsoever. Click on graph, and that's the graph for us. All right, and the graph looks just like the one that was generated with Desmos. All right, so Desmos gave me this graph in red color because Desmos chose that color by default, and I want to stay with that. But on the calculator, on the graphing calculator by default, or we actually chose to input 3/2 X on the blue graph like that. All right, and then with this graph, you can also change the window and the zoom setting so that we can fall into somehow a square scale, and this is indeed already a square scale right here. All right, so let's just simply zoom out so that the graph will look closer to the actual graph we have seen in our from Desmos. So let's zoom out. Okay. All right, so now in a more zoomed out version, the graph now looks a lot like the graph we have seen back in the Desmos graphing utility on a web browser right there. All right. All right, and this is now something that demonstrates the TI-83, 84 with an older version of the operating system software right here. So now I'm going to go y equal to input my functions, and you can notice now that the print resolution is a lot lower quality compared to the latest version of the operating system software. But that should not impact our work. That should not impact the result. It should work exactly the same, and even the way how we get there is the same. So I clicked on y equals. Now the older software of the TI-83 and 84 calculator handles a less number of functions, can only graph a less number of functions at the same time. And here I see only 7 available one. Okay, but now we're going to go in parentheses 3/2, close parentheses, and raise power. All right, and this is what I was talking about earlier, that when we are using an older system, it won't bring us into superscript mode, so it stays just like that. And now we're going to type in X. So 3/2 X, 3/2 in parentheses X. This is how we type in our function. 3/2 to the X into the TI-83 or 84 calculator, the older software like that. And I type it in Y1. Now for the older software, we also didn't have that color coding feature with each graph like that. So that's all we have. Okay. And so now once we've done typing in the function, we're going to hit graph. All right, and the graph is even lower, in lower resolution compared to the graph we have seen in the later software of the TI-83 and 84 calculator. And then here it's not in square zoom, it's only in standard zoom, so we can go zoom, okay, and we can adjust that by select option number 6, say zoom standard. All right, so now it put the graphs in standard zoom 1 by 1 like that, so that the graph can be more on scale. So this graph now looks like the graph that's shown with our Desmos or graphing utility. All right, so that's the one with that. All right, so after having a good amount of time spent on how to navigate around with the technologies, let's apply our steps there, but this time I'm going to move on a lot faster. So now let's call that the part B of the example. So we still want to use our favorite graphing utility, any one of these. We don't have to use both. So part B right here, let's look at the graph of, how about the function f of x equals e to the x. All right. So now this is our function, okay? And I purposely brought this in, and I want to show the technology with this because any technology has an actual one special button for this, okay? All right, so back on my Desmos, notice this is currently the graph for 3/2 x from our previous problem of the example. And we can still keep that here. We don't have to delete that out, but instead I'm going to hide it out. So how about I'm going to call that g of x this time. On Desmos, I'm going to name it slightly differently, so g of x, or a different function right here. So now I'm going to delete this out, okay? For Desmos, it's as simple as just typing the number e, the lowercase letter e, and that's, for Desmos, Desmos is understanding this as the value 2.718. Recall from our introduction lecture that I introduced e here as a constant 2.718. Aside from that pi constant, so e is a constant that's well known in the modern math right here. Okay, so now e to the x, so we just simply type e lowercase e. Desmos already recognized that special letter e right there, and indeed for Desmos, e is reserved for that special constant right there. So don't use e for any other purpose actually. Okay, so now e raised to there, so hat key, and that put me in the superscript mode to the x. Okay, and I highly recommend any users to learn those habits, that exiting out of superscript mode. So you can, from superscript mode, either you hit the right arrow key to get out of that, or you can just simply click anywhere outside. Okay, that gets you out of the superscript mode like that. But now this is the e to the x. All right, so e to the x now is printed in green. Okay, e to the x is printed in green. And now, since we're doing along that way, let me quickly put back that 3/2 x we have seen in part A right there, in red. So 3/2 x is here. So as far as the value of the base, it's a little early to introduce this now. But the base here in the earlier function for f of x in part A is 3/2. Numerically speaking, it's only a 1.5, whereas this e is a 2.718. So the base here is a lot higher. So look at how it changes the shape. The two functions being put together here already on the screen that you are seeing, the two graphs being put on the screen together here, the green and the red, but one of them is, and they're all in the same shape, going one way, rising one way from one side to the other side, going one way. And I will get more specific about what it means by being going one way. But see, looking from the left to the right, the two graphs here are both rising from the left to the right, rising from the left to the right. Okay, but now the graph in green is rising much faster in that right hand side of the y-axis, whereas the graph in red right here, it's also rising, but rising not as rapidly as the green one right here. So the value of the base the value of the base has some explanation for that, and we will get to that. All right, so now the graph in green is officially the graph for e to the x. And that's my aim here, mainly to show how we can use the technology to get the graph of that function. All right, so now back on my graphing utility with the TI 83 or 84 allow me to stick with only with the latest software version. So here I'm going to go y equal, okay, and now allow me to still keep this function just like how I was doing that on Desmos here. Allow me to still keep this with the work from part A right there. So now I'm going to pick a different function. I just also want to show that we can use the same software here, the same calculator to plot multiple, to graph multiple functions, multiple curves at the same time. So y2 here I'm going to go e to the x. So e to the x is indeed your calculator has one button right here. E to the x is found right here. Okay, there's the ln button, so the e to the x is right above that. So to access that feature, we go second ln. All right, so now it's e to the x. So it made an e constant ready with a superscript mode. So this superscript mode is for the advanced version. Okay, so now we're going to type in x. All right, and that's how we finish with the e to the x, how we finish inputting e to the x as another function. And so when we see that on the graph for this will be color-coded in red color. Okay, and the graph will display two graphs here. All right, and again, for anyone using this advanced, this most latest software of the TI-84 calculator, I highly recommend to exit out of the superscript mode. Currently, we're in superscript mode right now. Click the right arrow key. That exits out of the superscript mode. All right, and now we can just simply hit graph. All right, and so now this is the graph of the two functions. So the one from our part A, the work from our part A is in blue here. This is 3/2 to the x. And this in red right here is e to the x. And the result here is exactly consistent with the result we have observed when we were using Desmos earlier. So the graph in red here for e to the x is a lot steeper, is growing a lot more rapidly compared to the on the right hand side of the y-axis compared to the blue version. All right, and we will get more to that when we further progress into the understanding of the graph of any exponential function. All right, so that is how we've learned. That is how we use the graph to get to quickly get. Use a graphing utility to quickly get the graph of any of these exponential function. Okay, and that way of using the graph, using a graphing utility is also the same way of how we can get the graph for any other kind of function. Here in this particular lecture, we are working with exponential function. So we input, the only difference with other graph is we input an exponential function, and then we get the graph for exponential function. Okay. All right. So now that we have learned, we have seen how Desmos are. We have seen how Desmos are using. We have seen how we have quickly pulled up the graphs for our function from Desmos and also from the TI 83 and 84 calculators. So I'm going to come up with the following activity where we're going to completely stay on a graphing utility. I stay with Desmos for my lecture over here, but you can also use your own favorite technology. Okay, but for the fast purpose right here, and good resolution of the graph, I stay with Desmos. Okay, but let's explore. Because the graphing utility is so powerful and it can quickly get us the graph, so we're going to use a graphing utility, okay, to explore and start putting some further conclusions, okay, some further conclusions regarding the graph of any exponential function. All right, so now on my Desmos here, I have prepared quite a few exponential functions being listed on the command entry line right here. Okay, and since Desmos is so powerful, I stick with Desmos to quickly pull out the graph here. Okay, so this is what I'm about to do. What I have here is a list, and I already hid away all the actual graphs. I only have the function being inputted here on the left hand side panel. And further, you can see that I purposely put these in increasing order from the bottom up right here, or decreasing order from the top down. Okay, and so allow me to first show the graph of the 2 to the x. So I'm going to click on that, and this is the graph of the 2 to the x. The graph of the 2 to the x. And we have seen this graph even earlier in that earlier lecture before this lecture when I was introducing the basic idea of an exponential function. So this was the graph we have seen even in the earlier lecture, and now we're seeing it again. So for now, for this very first graph, let's look at the shape. Again, it's just nothing unusual once we have seen it already. If we're looking from the left to the right, the graph is going one way. And one way now to me means it's not having any turning points. So we have learned about the polynomials and the rational functions before this kind of function, the exponential function. So polynomials, any polynomial has that fascinating feature where the graph's going up and then turn down and going up, going down and zigzagging way all over. This function 2 to the x is going only one way, going up. Well, for now, for this one we're currently seeing it's only going one way, going up. So on my screen right here I'm seeing that way, but maybe my hand drawing is a little opposite with what you were seeing right there, but it's only going one way. All right, and so now let's get back with Desmos, and I'm going to now put in, how about the graph of 3 to the x. We have seen this one earlier. That was part of our example that we've done earlier. So 3 to the x compared to 2 to the x, it has a larger base, that's all. And of course, just like what we were learning earlier from the introduction to the exponential function, now the base of any exponential function has to be a positive value. Okay, and so in that way, now on the graph again, 3 to the x has a positive base 3, 2 to the x has positive base 3, 3 to the x is in green color, 2 to the x is in blue color. Okay, and then notice the change here. So they're both being similar. They're both similar with each other in a sense that putting the two graphs together, they're both going one way. So the left is low and rising rapidly to the right hand side of the graph. Okay, so the graph itself, what it's showing there is that it's going low on the left, and it's going rapidly rising on the right hand side. Okay, that's the similarity of the two graphs here that we're seeing. All right, so that's what we're seeing with the two graphs here. Okay, so now let's put in some more. Okay, so now I'm going to show the graph of the 4 to the x. All right, so the 4 to the x is this graph in blue right here. The 4 to the x is the graph in blue. Okay, and so again, it's the exact same feature. It's just going one way. It's low on the left of the y-axis and it's rising, and it's even rising more rapidly. So now let me put it in even a closer zoom so that we can see how quickly it rises. Okay. So the graph in blue rises even a lot more rapidly compared to these. So when I'm saying rising rapidly, I mean think about one vertical grid right here. Okay. Then the red version here is only 2 here, and then the green version is a lot higher, and then the blue version is up to 4. And then on this side right here, it's going to be a lot flatter down right there. But in the end, all three graphs, as long as the base, so right now we're recognizing the base I'm sticking with, those bases that I stick with, they are those bases larger than 1, 2, and then 3, and then 4. Okay, and then so it seems like what matters is just gonna get more rapidly on the right hand side and more rapidly on the right hand side right there. All right, and then a little more into the graph right here. Now I see all three graphs I brought up so far all going through this one point. This one point right here is at let me put in that special point right there, 0, 1. Yes, we can call this the y-intercept, because it's going right through the y-axis. Okay, 0, 1. All three graphs so far, and it's having that structure right there. that one way rising from the left to the right, okay, and low on the left and rising rapidly on the right. Okay, one way rising if we're looking at the blue version. Okay, one way rising, low on the left, rapidly on the right. Okay, and then now so 3 graphs so far, they're all going through that point. So now I do plan to pop in the graph for 5 to the x. You can already start having some expectation of what the graph will look like and in whatever color it will come out to be. All right, so now here we go. All right, so in cyan color right here, or orange color, the graph came out just now, orange color. The exact same shape that was expected. So now allow me to hide away the other ones. So the shape remains exactly the same. It's also going through that special point at 0, 1. So 4 graphs all going through that same point. Okay, all going through that same point, that same y-intercept at 0, 1. All right, so 4 graphs so far being like that. So now let me hide away these extremely high bays right here. And we're still sticking with those bases being positive. So what about when the base is not so nice looking, like a 2.1? Okay, or maybe here, let me change to an e to the x right here. Okay, I changed my mind. So 2.1 is here. So 2 is here. 2 is the red version. And then 2.1 to the x is the black version. Okay, and the 3 to the x is the green version. It's the green graph. They're all going through that 0, 1. And now, even if we put in that e to the x, the base is completely irrational. It's a 2.718, and we never finish the decimals. Okay, but and the color is in purple over here, but it still has that exact same shape, and they're all graphs going through that point. All graphs going through that y-intercept being 0, 1. All right, and so now we're still looking at those bases above 1, but now let me move down to those bases slightly below 2. Okay, slightly less than 2, because it just seems like I started out with 2, with base 2, a base that's already greater than 1, and then I keep looking at those bases higher than 2. But let's look at this 1.5 right here. So it's still going one way, and going through that y-intercept. Okay, at 0, 1, and the base here is still above 1, still greater than 1. Okay, and now I'm gonna pop out another base. Okay, another base that's closer to 1 but still greater than 1, 1.25 to the x. Okay, and so now notice the change here. So now it's become flatter out and flatter out. The blue is for 1.5 to the x. The green is for 1.25 to the x, and it's more flatter out and more flatter out. Okay, but it's still going one way, and the right hand side is still more rapid than the left hand side. And when I say right hand side and left hand side, I meant the right hand side of the y-axis, or the left-hand side of the y-axis. All right, and so now that's the picture. Now that's the y-intercept, and I'm even gonna put another value. I'm gonna even put in another value, 1.05. Okay, it's still above 1, still greater than 1, but a lot closer to 1. And look at what happens. It's still that shape right there. And so now, how about let me hide away these the easy noticeable ones. Let me just stay with that, the 1.05 to the x. Okay, and now I'm going to purposely zoom it out. And so we're going to notice, yes, the right-hand side grows, is rising again more rapidly than the left-hand side. And this is, but for a base being this close to 1, then and we have to put it in a really far zoom in order to notice some change like that. All right, and so now if we're putting that in the usual scale where we see 1, 2, and 3 on our scales, and it looks almost like a tilted, flat line right there. All right, so now at this point we are ready to make some generalization. Okay, so all of those graphs you've seen, all the way from anywhere slightly above 1 with the base, of course positive base, but anywhere from the base being even slightly above 1 to, we went to as high as 5 already. Okay, and thankfully we have that Desmos so that it can quickly pull out so many graphs, and we can instantly put them side by side so we can compare their behavior. So as a generalization now, this is what I see. For the base being, of course, base is positive. Okay, so for any base being greater than 1, so recall from what we saw with the Desmos graphing utility screen right there. The base went to as, I used the base to as high as 5, and then to as low as 1.05, but these are all greater than 5. And so the graph generally has something like this, was a shape like this. So now at this point, when we completely let go of a specific value of the base, we just look at f of x equals a to the x, where the base here is a value positive and greater than 1, then we know for sure that any of those graphs had a y-intercept right at 0, 1. Okay, right at 0, 1. And then it going like this, rising slowly, but then rising rapidly. See, and I'm not even sure which curve, which base of mine, which base is this one anymore, but I'm sure the base here, the shape here has to be the shape of an a to the x, where the base is greater than 1. Okay, so it's rising one way and rising from the left to the right. The x-axis is here, the y-axis is here. So that's commonly the shape for any exponential function where the base is a positive base and greater than 1. And of course, we always work with positive base. All right, but in that way, just think about now. So here for the formal pre-calculus students, okay, for the formal pre-calculus students making your way, learning your way up to prep yourself for a formal calculus class. Let's look at something like this. You see, well, needless to say, the picture right here, either as a hand sketch version or through the graphing utility, is showing it already. The right-hand side will keep rising up higher and higher. For this particular case, where the graph, where the base is greater than 1, the right-hand side is keep rising. Now I'm talking about the and behavior. Okay. The and behavior. For this case right here, the and behavior, so as we let x approaching or tending to the right-hand side, then the graph, as we navigate, as we're heading out on the horizontal axis, as we're heading out to the right end and the further right end, our graph vertically rises and rises and rises. All right. So this idea was introduced long ago in our learning time, in our learning quarter here. The function f of x, the outputs, the vertical value is going to the positive direction, rising, going up. So this is positive infinity. See, the y value is going up. All right, it's going up. And then in this way, so now I'm talking about the and behavior. Just now I was looking at the right and behavior. This was, we once learned that this was the formal symbol, formal notation to indicate that we're currently investigating right and behavior. Okay, so now what about the left and behavior? Think about any of the graph we have seen on the Desmos like that. Maybe one more time, let's swing back at Desmos. All right, so on Desmos here, this is 1.05 to the x. Okay, this is 1.25 to the x. All right, and this is 2 to the x. And maybe I'm going to skip out a few. Okay, and then this is e to the x. And then how about 4 to the x? 3 to the x, 4 to the x, and 5 to the x. Okay, so those are... All right, so those graphs. Now, if we're looking at these graphs on the left hand right here, as x is getting further out and further out to negative infinity, as we are getting further to the negative infinity on the horizontal axis, look at what happened. We will never find a part of the graph that sinks below the x-axis. Again, what I was saying, looking at the way how the picture is, how about let's just turn away any of these, hide away any of these, just keep one. So for a graph like this, an exponential graph, base greater than 1, okay, we already knew that we had an intercept, a y-intercept right at 0, 1. So now if we're looking at further out to the left end of the graph, we will never see any portion of the graph here being below the x-axis, see? And now if I zoom it in, if I put in a really close zoom at x equals negative 18, for example, eventually at some close zoom enough, we will notice a difference, okay, where the graph in red is above the x-axis. Okay, so the graph, it is completely legal. All right, so for the graph, for the function, it is completely legal to say that as we getting further to the left-hand side, the graph will always stays above. The graph will always stays above the x-axis. Okay, so for 5 to the x, for example, see it completely stays above. Even though from a far zoom like this, we see almost no difference between the graph and the x-axis. But as a matter of fact, it still stays above right here. All right, so now in that way, we can make our conclusion as x is tending to the left-hand side. Okay, as we're investigating the left-hand side. See, the truth is the graph, the vertical value comes down to 0, comes down to y equals 0. It comes down, getting close to, but it will never hit. So I'm only saying it comes down to, but it will never get down to that line y equals 0. So I can say the vertical value gets close to 0. Okay, gets close to 0. See, it gets close to 0. It's coming down to 0 like that. Okay, but then you have to also keep in mind, this is one thing. This is permanent right here. This is something permanently happens. The y value is always positive. It's the way how any of these exponential function has to be permanently. Right now we're particularly investigating the case where the base is greater than 1. Okay, and then the graph is permanently above the x-axis. But on the left end, it's getting closer and closer to the y value. Okay, so now at this point, we have seen that idea earlier when we were studying about a rational function. We can start using that term again. So in this case right here, now I can say that we can take a note here. This is an observation. Okay, when the base is a value greater than 1, the exponential function a of a to the x right here has a horizontal asymptote. Okay, at that line y equals 0. So y equals 0 is the horizontal asymptote for this function right here, for this simple or basic exponential function a to the x, where a is a value, for now, a is a value greater than 1. All right, so that's one case right there. So immediately as I finish with this case, your major mind in math now at this point will start coming up with that curiosity question. What about when the case, well, of course we won't go with negative base, so that's out of consideration. Okay, but you're going to start wondering, so what about when the base here is equal 1 or less than 1? Is equal 1 or less than 1? It's equal 1 or less than 1. So on my other board space right here, I'm going to quickly write this down as a note on my scratch right here. We already ruled out that the base cannot equal 1. All right, so yes, as a curiosity, maybe because we forgot. So mentally we would ask, what happened when base equals 1? I will have some I will put together these graphical understanding and put it in as an explanation later on that why we exclude x equals 1. I mean, why we're excluding out the base equals 1 in our family of exponential functions. But now, assuming that we already were aware that we exclude base equals 1, then the other case left is when our base is any value less than 1, but still, of course, positive. So now we want to head into that way. What happened to the graph when the base is less than 1? What happened to the graph when the base is less than 1? All right, and so now, back on our empty graphing space with Desmos here. So let's start out with 0.9. Okay, so 0.9 to the x. So clearly this is reflecting the case where the base, positive base, but less than 1. So 0.9. So this time, and let me zoom it out further. All right, so this time it looks like the shape is going in the opposite way. All right, and so now Let me also show the base being about 0.75 in black. Okay. So the base now this time, with these bases being less than 1, what we notice so far throughout the two graphs being put on the screen right now is that it's still going one way. It's still going one way, like how we have seen it, but it seems like it's going the opposite way. An opposite way in a sense that it's going from high and it's dropping low and it's dropping low. The drop, it was dropping rapidly and then it's dropping low as it gets to the right hand side of the y-axis. Okay, so again, right here on the graph, it came from high value, some really high value, and then maybe it's not that high, but then it keep getting lower, so it's falling from the left to the right. Unlike the case where those cases where we had base greater than 1, here when our base is less than 1, it was a fall. It's falling steadily from the left to the right. It keeps falling. Okay, it's falling continuously from the left to the right. Okay, and then the 0.5, which is the same as a 1/2 to the x, is this graph right here. And we indeed, if this is the same as a 1/2 to the x, we have seen this in our graph earlier. That's when we were doing that graphing sketch activity. And now we don't need to pull out too many of those, but let's just look at one more right here. How about 0.25 to the x? All right, and in blue ink right here, 0.25 to the x. So all four graphs where the base is less than 1, positive base but less than 1, then we are seeing that they are falling from the left to the right. The part on the left, opposite from the earlier case where base was greater than 1, the part on the left here now is falling a lot more rapidly. So it falls rapidly, and then the fall is slowing down right here. So the fall itself is slowing down. All right. So now at the y-intercept, they are going through that same y-intercept again, 0, 1. All right, so now after seeing 4 graphs here, that should be enough for us to put in some conclusion. Okay, so now here on our graph with all of those functions, yes, it's an exponential function again, but where the base is less than 1 this time. This is what I noticed. This is what I saw right here. Okay. Instead of rising from the left to the right, now the graph is falling from the left to the right. Falling from the left to the right. And just like that, the fall is on the left-hand side of the y-axis. The fall is a rapid fall, and then once the graph goes past the y-axis, the fall becomes less rapid. And as a matter of fact, the fall is now a slow fall. Okay, it's only slowly falling. All right, and so in that way, now also any graph that we've seen on the Desmos graphing utilities earlier has that y-intercept at 0, 1 again. All right, and so now it has a lot of similarity with the earlier case where the base was positive, but now the base is, when the base was negative, when the base was greater than 1 earlier, it has a lot of similarity with this. So the similarity is in the sense that they are having that they're going one way. The only opposite thing when the base was greater than 1, the only different thing was that the graph was going up like that. Okay. So when the base was greater than 1, so we are working with positive base, but when the base is greater than 1, the graph was going one way and rising from the left to the right. Okay. And then it's going through that y-intercept at 0, 1. All right. So now, in the case where it's a base being less than 1, then it's still going one way like the other case, but the graph is falling. That's the only thing being opposite. Okay. And then it's still going through that y-intercept at 0, 1 right here. And so now let's look at the end behavior. So this is one more thing that makes it opposite from the case where a was greater than 1 right there. So let's look at end behavior. All right, so for end behavior, now this time as x is tending to the right-hand side, positive infinity. Okay, when x is getting further to the positive infinity side right here, to the right end, when we're approaching the right end of the graph, heading out to the right end of the graph, and what seems to happen to the graph? What seems to vertically happen to the graph, or the vertical values of the graph? The vertical value of the graph, this is what f of x is for, vertical value of the graph seems to keep dropping. But we never spotted, throughout the 4 graphs I've had on the screen, we've never spotted any part of the graph where it fell below the x-axis. So in other words, another way of saying, the vertical value decreases or approaches, getting close to, that's why I'm using this arrow pointing down right here, but should be only dotted arrows, approaching 0 on this end. Okay, on the right end, the graph gets close to 0. The vertical value gets close to 0. Opposite with the case where the base was positive 1, then the graph was rising up. Okay, was rising to positive infinity as we're tending to the right end. Okay, and then so now back on this case right here, what about the left end of our graph where the base is less than 1? Now as x is heading to negative infinity, the graph on the left end is rising vertically, so it's going to positive infinity, because now if we're heading out that way, the graph, see, if we're tracing on the graph heading to the left hand side, the extreme left hand side, then the vertical value is going to keep rising and rising and rising. That's what this arrow symbol means right here. All right, but in the end, another generality that's similar to what we have seen on the other board. The graph permanently stays above the x-axis. The graph permanently stays above the x-axis. So now I have to say it. I have to emphasize that again. Permanently. All right. Permanently, we have y value positive. It won't even be equal to 0. Okay. It won't even be equal to 0. Y is positive permanently. Positive, but it does get closer and closer down to 0. See, no matter how far we go, it's just not going to hit equal 0. It's just going to get closer and closer to 0 like that. All right, so in that way, we're using that term again as a general conclusion, as another conclusion. F of x, okay. This case also we recognize f of x has a horizontal, okay, asymptote. All right, at y equals 0. So this line, I wrote it in red because it's a specialty. Now we all of a sudden we recognize for base less than 1, currently we're looking at the function here. This function a to the x has a horizontal asymptote at y equals 0. It's also the same here when base was greater than 1. That function there, those graphs there also has a horizontal asymptote at y equals 0 right there. Okay, so it looks like now it's a common property regardless of what that base is. The function, the a to the x function will have a horizontal asymptote. The simple a to the x function will have a horizontal asymptote no matter what. And then this feature was common for both cases when a was greater than 1 or a was less than 1. Okay. The value for y stays permanently positive above 0. All right, and then going one way, either going up or going down. Okay, and then going through that y-intercept at 0, 1. 0, 1 is here. Also 0, 1 is here. Okay, so now from putting the two cases side by side together, we can start forming some generality right there. Some generality. So we have any a to the x right there has that, any simple a to the x, coefficient 1 here, okay, and then just a to the x, regardless of whatever base, as long as it's positive, as long as it's a positive number, then we have a y-intercept at 0, 1, and it has a horizontal asymptote, okay, horizontal asymptote at y equals 0 right there. All right, and then of course the graph permanently stays greater than 0 for that simple case right there, for that case a to the x. All right. So right from that conclusion, we are ready to put in some example. All right, so now just with the understanding about the base and how the base affects the shape of the graph in general, that after we've learned the two different cases, it's enough to come to look at this common kind of problem right here, and it's given throughout many textbooks out there. Okay, so let's bring it in as our example 3 right here. Let's just match, okay, each given function. All right, match each given function with the color of the graph. So we're going to match each given function with the color of the graph. I didn't put in the functions yet. I didn't put in the graph yet, so you probably completely unaware, I mean clueless at this point what I mean by what it's meant by, you know, with the color of the graph. But this is how. So on the board here, I'm going to write down a list of about 5 exponential functions. So A, and this is a little bit unlike the usual case. I'm going to write all 5 functions here at A, B, C, D, and E, and F. Okay. So A here is a 1.5 to the x. Okay. B is 0.75 to the x. C is f of x equals about 3.25 to the x. Okay, and then we have D. We have f of x equals 0.25 to the x, and E here we have f of x, okay, equals 2.5 to the x. Okay, so what I have here really, it's not 5 separate problems, it's really just one problem, but what I have here is a list, A, B, C, D, E, 5 different functions, 5 different exponential functions of different bases. Okay, some base is above 1, some base is below 1. And that's all I see. And these are all in those basic form, a to the x, and a is a positive number. That's all we need. And so now along the way, I'm going to pop in a picture. I'm going to now put in the picture of 5 different graphs. So they're all graphs of these, but each one of the graph is having a unique color. So we have to match which graph here is that in blue, in red, or in pink, whatever is the graph for 1.5. Which one here, the blue or the red or the black, is the graph for 0.75. That's what we need to match right there. All right, so now for starting out in completely in full screen view right here, allow me to show for a little bit, that's the 5 graphs in full screen view right here. So we have a graph in blue color, we have a graph in purple color, we have a graph in red, we have a graph in black color, and we have a graph in green color. So 1, 2, 3, 4, and 5 different colors. So these are the graphs from our different functions here. We need to make a match. Okay, which one, the blue or the black or the green, is going to be the graph for the 1.5 right here. All right, so that's what we want to investigate. So now the key to be successful in this kind of problem, where like I said, it's a very common problem that's being asked by many different professors out there, and from many different textbooks. It trains your skill how to quickly, and the point is to do this without using a graphing technology. You don't want to pull out your own graphing technology, graphing device, and graph these things one by one and match with that, the one you see in the picture. That's not the point. The point is, from what we already generally concluded about the shape, okay, and the common characteristics of these a to the x function, we're gonna only use those. We're gonna only use those information as the driving key to answer this. So first of all, I spotted these are the ones where it's greater than 1. The base is greater than 1. These are the two, the 0.75 and the 0.25. They are the bases less than 1. So these ones right here have to be among those where the graph is going down like this. And we already spotted those. And then from there, we're going to start narrowing down our understanding. But for now, let's leave these two out for now. Okay, let's look at these. Bases being greater than 1. So I explained this earlier. When in that case where the bases were greater than 1, when the base was greater than 1, then the higher the bases, the steeper it is, the more rapidly it grows on the right hand side. See, so any of these has to have the graph. So on Scratchwork, the graph has to look like this, rising, and it all has that pointer at 0, 1. 0, 1 is here, but it's rising to the right hand side. Any one of these has to have that graph, that shape like that. All right, and then it has to rise, so it's going to rise even more quickly and more quickly, more rapidly and more rapidly as the base gets bigger. All right, so this is the lowest base value, and this is the highest base value, and this is the middle high value, So now with that information, the picture is telling enough story. So now let's look back at the picture. You have that here, but now I'm also going to pop it in full screen like that. All right. All right, so now in full screen mode, allow me to only focus to those that being rising to the right hand side. All right, so rising to the right hand side, I don't need to look at these one yet. All right, so rising to the right hand side, or maybe let's just still put it in, because in case we don't have that flexibility to hide away a certain graph, then we can still work with the worst case where we still have to physically ignore these and only focus on the 3 graphs that rising to the right hand side. All right, so again, keep in mind, the higher the bases, the more rapidly it grows on the right hand side. The higher the bases, the more rapidly it grows on the right hand side. So now in that case, it looks like this green version, this green graph right here on the one of those that the base is greater than 1, this green graph grows most rapidly. Okay, see, how can we detect that? Now think about, we put a vertical line here. Then so on the same vertical line at one horizontal x value, as one x value right here, this green curve gives the highest y value compared to the black and compared to the red. And I'm completely ignoring the two blue and the purple versions right now. All right, so in that way, the answer is now clear. Green here has to be for 3.25. All right, so now on my board, 3.25 is the green graph. So I'm going to do this. I'm going to draw that with green color. That's green. All right, we've had that. Okay, and then the next highest one down the list is this 2.5 right here. All right, and we saw on the graph earlier, it was the black graph. Okay, the black graph was the one that's being the middle high one. Okay, so now this one here is the black one. The black color graph like that. All right, and now with this one here being the last one, so it's going to have to be the red one. All right, so now we had that the 3 functions already matched successfully with the graphs. All right, so let's see what else is out there. So these 2 left, they're all having bases less than 1. Okay, so now we're going to focus on this right here. Now we're going to focus on these, the blue and the purple, Okay, the blue and the purple. So now back in the notes that I'm still having on the board here. anytime the base is less than 1, the graph is going this way. So that agrees with the shape we have seen earlier. Okay, that agrees with that shape. Further, we know, I could have also mentioned this, but I a little bit assumed a little bit that you already recognize that. But see, when the base is closer to 1, so we are talking about the base is less than 1. But if the base is closer to 1, like 0.9 or something like that, okay, like a 0.9, then the graph is actually more flatter. And then when the base is closer to 0, when the base is closest to 0, like down to being smaller and smaller, down to like a 0.25 or 0.05, something like that, then the graph grows more rapidly or falls graphically on the left. The graph falls graphically on the left as the base gets smaller. Okay, the demonstration is here. All right, we saw that right here. This purple one is a 0.9 to the x, and the graph looks so flat out. Okay, and then so these are all bases less than 1, but I purposely arrange them in the order where it's getting smaller and smaller and smaller in the base. So the smaller the base is, the more rapidly it falls on the left-hand side. All right, so that's another generality that we can see in the world of these exponential functions where base is less than 1. All right, so drawing out from that conclusion, from that generality. Now back in our problem, we have 0.75, okay, and let me bring in the picture. All right, so the blue is flatter compared to the purple. The blue is flatter compared to the purple. Okay, the purple is, in other words, the purple is more rapidly falling. All right, so smaller base, larger base. These are all bases less than 1 right here, but it's even smaller. So this one here has to be the purple. All right, that one there has to be the purple. And the last one now that we still have on screen right here. The last one now, 0.75. Needless to say, the rule of exclusion. We have excluded out all the other ones. This one left has to be the blue version. Okay, the blue graph has to be there. All right, so that's how we can see. I only relied on the understanding about the base, either less than 1 or greater than 1, and how large that is or how small that is, and it already gave all of that explanation. Because all of these graphs here that you're seeing, they're all going through that intercept at 0, 1. Okay, and that's how we can successfully get through with this. So a lot of thought process was being displayed here, was being shown here. My thought process are all being shown here. And so it seems to slow down your process a little bit. But when it actually gets you doing these kind of problems, it should be a lot faster. Okay, and once you keep working on this kind of skill right here, okay, then it's going to get a lot faster. All right. All right, and so now, at least in my style of teaching a pre-calculus course, then transformations to a graph of a function must be learned before we specifically get into the learning more specifically about any kind of function. Like we learn about transformations in this course, we learn about transformation before we learn about the polynomial functions, before we learn about the rational function, and even before we learn about what now the exponential functions. Because transformations is the idea that can generally exist on any graph of any functions. Okay, so it really has been a little while since the last time we have seen transformations on generally any graph of a function. So I just want to remind anyone learning in this lesson, all of those transformations that we've learned, we apply on the graph of an exponential functions as well. Okay, on the graph of an exponential function. So all of those transformations. But we won't have to emphasize as much on the transformations at the end of the lesson here under all the graphical details about the graph, I will get back and do some more transformations. But now allow me to introduce just one brief example where we're going to see how we apply our past understanding about the transformations into the graph of an exponential function. Okay, so we want to see the transformation. So here, I just want to remind anyone, so before we get into this, we just want to see that, hey, how the transformations can still be applied here. Okay, so let's now call that example 4. Okay, so now we want to, so I use the word sketch the graph. Okay, I use the word sketch the graph, but really I don't intend that we have to do this by hand anymore, but it's just to remind you, or at least it gives you, once we're done with this example, it gives you a good sense about what to expect when we see the graph, when we recognize the function here as a transformation of from some other parent function. Okay, but so I'm still trying to move on to be as closely as possible to like how we were sketching that with paper and pencil, but really I don't intend that anyone, at least if you're learning with me, I don't intend that anyone has to do this by hand sketch anymore. Okay, so that's just to remind you, this example completely comes as a reminder that we still can apply the transformation that we've learned previously, okay, into the graph of an exponential function. So let's sketch the graph of the given function as following. So how about g of x that I sketch here is about 2x, I mean 2 times 3 to the x minus 1. 2 times 3 to the x minus 1. Okay. 2 times 3 to the x minus 1. And so if we recall from our understanding, from our learning about the transformations, we have to first identify, because you see, here's how I see it as a thought process. This function has things all over. It's not just simply an exponential function like what we've been working with earlier. It has a lot more in that. But now if we're breaking it down one by one, this is what I recognize. Let me now narrow down your attention or your focus right to that 3 to the x. If we just focus right on that 3 to the x, then it looks like we have a parent function. It looks like we have a parent function being some f of x, being defined as the 3 to the x function. Now that, at this point, we should know immediately what to expect in the graph of a 3 to the x. It's a base being greater than 1, positive base, of course, greater than 1, and so it's going a one way up, right there, one way rising from the left to the right. Okay, that's what we can expect immediately already. Okay, and then we, as a matter of fact, we have seen the graph of this one. We sketched it by hand in example 1 of this lecture right here in this particular video recording. So now, how is this g? Now, when I was lecturing, when I was giving that lecture about the transformation, I refer to g as a descendant function out of that parent function. So the parent is here. How do I see g as a descendant of the parent function? Okay, and so now once I isolate it out, and here's what we further recognize in terms of the operations. See, the order of operations says if we're having a function like this, then we have, for any input x, we have to raise 3 to the x first. See, according to the order of operation, we have to handle 3 to the x first. And then, once we have it done, we can multiply the result of 3 to the x, the outcome from 3 to the x, with 2. We multiply 2 to the outcome of 3 to the x. But 3 to the x has already been isolated or recognized as a parent function. So in that way, according to the order of operation, it looks like g to the x here comes out as the outcome of f of x, the parent function, but multiply with 2 first. And so now with our understanding about the transformation, this 2 right here now is a coefficient. It's a coefficient. And as a matter of fact, when in the earlier lecture right before this lecture where I was introducing about the exponential function, I also introduced those general or those extended. I introduced the extended definition of all general exponential functions out there. So we can a lot of times we can likely have a coefficient in front of our exponential. This is the case right here. So 2 multiplied with the outcome coming out of 3 to the x. And then that's minus 1. Okay, but see, this 2 now, with our understanding about the transformation, it's responsible for vertical scaling. It can make it vertically stretched or vertically compressed, okay, or even flipped, blended with some flip like that. I highly recommend that at this point, if you are going if your skill in transformation has faded away a little bit, go ahead and pause the video or exit out of the video and review your skills into transformations. Okay, and then aside from the vertical scaling here, we also have some vertical shifts. Okay, vertical shifts, bringing up or bringing down right here. So this is how I recognize g as a descendant from this parent function. So now as a label, the 2 is responsible for vertical scaling. All right, and then this minus 1 right here is responsible for vertical shifts. All right, that vertical shift. And so back at the lecture where I was explaining about the transformations, then I introduced that technique where we rely to the guiding points. Any graph has a certain number of guiding points. Okay, any graph has a certain number of guiding points. So in this case right here, let's see how it works. All right, so right here on the graph of 3 to the x, this is the graph of 3 to the x. Okay, and we can use those points right on the grids. We can pick those points as our guiding points, and we don't have to pick all of them. Okay, we don't have to pick all of them. Just a few is good enough. Okay, and so normally I would just pick right at those 3 points right here. So we have one at negative 1 comma negative 1 comma 1/3, and then 0 comma 1, and then 1 comma 3 right here. That should be good enough for an exponential function. Okay, if you would like more details, you can pick these 2 further ones, like say a 2 comma 9, and then a negative 2 comma, this right here is a negative 2 comma 1/9 right here. But it's for this particular function, it's hard to get that one. All right, but now these are the guiding points on the original parent function. All right, so I'm going to put that, combining with that table approach I was teaching when we were talking or learning about the transformations. Then let's do the following. The original parent function f of x has these guiding points here from the left to the right. Okay, I have 5 points, but like I said, only choosing 3 points should be good for us. So from the very far left, I was looking at minus 2, and that was comma 1/9. Okay, that's the original guiding points. And then minus 1 comma 1/3, and here 0 comma 1. Okay, and this is 1 comma 3, and this is 2 comma 9. That should be good enough for our work right here. So the next transformation that should come in is the vertical scaling, because, so once again, just a brief reminder, I don't need to go back all the way to the basic, because if you need the basic, go back to that lecture of mine where I had that massive information. So vertical scaling must come before vertical shift. Okay, so in that way, taking that down right now, taking that accounted right now, then now I'm going to have to produce one column for 2 times f of x, but that's not our final destination yet, but we're moving in steps. So now in what we've learned, then multiplying a coefficient to the front of the function, that just means, or at least for this kind of transformation, the vertical scaling, all we do is just multiply every y value by this coefficient, multiply every y value by that coefficient. So the coefficient can be positive or can be negative. The y value will come out, and it will drive the transformation. It will drive into the change in the picture right there. So now, multiply 2 to every y value. For y values are here. Okay, so nothing is done with the x values. So now that means in the next step right here, I'm looking at negative 2 comma 2 over 9. Multiplying 2, positive 2 to every y value. So now negative 1 comma 2/3. Okay. 0 comma 2, 1 comma 6, and 2 comma 18. All right. Quite large values there. Okay. And now the next step here is to produce so these are the guiding points after we multiply these. These are what the guiding points became after multiplying 2 to every y value. And now in the next step, I'm going to produce, so from the guiding points of the very preceding step right there, I'm going to move on to our last step right here. So 2 times f of x minus 1 right here. Okay, that gives me, so once with this shift right here, the easiest way that I introduced, subtract 1 from every y value. Subtract 1 from every y value, and this is our last one of the transformation, our last step of the transformation. So I'm writing that in blue right here because it's just a habit I was doing about the transformation. Okay, so now here I'm looking at, it was minus 2 comma 29, but I'm going to subtract 1 from every y value. So minus 2 comma negative 7/9. All right, minus 2 comma negative 7/9. Okay, and then the next one here, negative 1. So that came out because I subtract 1 from 2/9. The next one here, negative 1 comma 2/3, now becomes negative 1 comma 2/3 minus 1 gives me a negative 1/3. All right, negative 1/3. So once again, nothing happens to the x values. Only the y value gets subtracted by 1. Okay, and so now the next one here becomes 0 comma 1 because I subtracted 1 from that y value and nothing happened, nothing done to the x value. And then the next pair of value right here becomes 1 comma 5, and the next pair of value becomes 2 comma 17. So these are our final points right here. All right, so now let me bring that on screen to see how it happens. All right, so now with my Desmos graphing screen right here, this is the graph for the original parent function, 3 to the x. And as I said, I'm not going to follow as closely with the sketching work as much as the time we were formally learning about transformations anymore. But these are the guiding points that I chose. 0 comma 1, 1 comma 3, 2 comma 9. And I chose negative 1 comma 1/3 and negative 2 comma 1/9. Okay, so now with the graph, so now these are the plotted points for the transform version. All right, so in blue, this is the graph of the transform. This is the plotted points of this is the guiding points on the transform version. So we still have that point at 0 comma 1, but that final point there's a 1 comma 5. And we also have one at, I'm not at the far zoom level enough, so let me zoom it out a little more. Okay. All right, so I have another one. So let me put back the labels in. 1 comma 5, and I have another one at 2 comma 17. All right, so these are the final guiding points right here in blue. And then we have another point right here at negative 1 comma negative 1/3 right there. And then we have another one right here at negative 2 comma negative 7/9. All right. So now with these plotted points, all I do is just put the graphs through. Okay, and the graphs here is like that. So all of the expectations are here. We expected that the graph was being, first of all, scaled up. Okay, so right from here we can still see that it has that y-intercept right there. So think about it's all gets stretched out by 2, by a factor of 2, and then it gets pushed down. Every y value was multiplied by 2, and then it gets pushed down. It gets shifted down by 1 unit, and that's why now in a closer zoom, we can see that with this graph right here, in blue. Now the graph in red from our previous understanding. Now let me hide away these extra information first. But from our previous understanding, this is the graph of 3 to the x. So the parent function has to have this horizontal asymptote at y equals 0. Okay? And now for our function, being 2 times 3 to the x minus 1, the parent's function multiplied by scale by a positive 2 but subtracted 1. Okay, subtracted 1. So let's look at the graph one more time. All right, so now with the graph here, the guiding points are being placed here, and with the graph being displayed, it looks like the graph in blue here, the descendant function, has the asymptote down to as low as y equals negative 1. All right, so it's just an extra note that we put here with our particular graph right here. Okay, so this function as a conclusion, we notice, okay, it has, so this function, so let me erase this extra note right here. Okay, so the final note I want to indicate here, g of x, right, as the descendant function has a horizontal asymptote, or how about 1 horizontal asymptote at this time y equals negative 1, and that came out from this value. And so we start having, I didn't want to get into formal generalizing that idea yet, but we will get to that idea. Okay, but right now I'm seeing this problem completely as a transformation, and so look at that, what that transformation caused to the horizontal horizontal asymptote right here. It shifted that horizontal asymptote down to y equals negative 1, because otherwise generally right here this graph has horizontal asymptote at y equals 0, as we already learned, but now the horizontal asymptote is shifted down to y equals negative 1. All right, so in that way, let's head out for part B of our example. All right, so part B of our example. Once again, another one where we come up with a sketch, but really, yes, ideally it's best that we go through a hand sketch again to recall our skill, but really it's not intended to go that far, that deeply into the hand sketch anymore. Okay, so we want to sketch the graph for g of x equals, how about just 1/2, minus 3 times 1/2 to the x plus 1. Minus 3 times 1/2 to the x plus 1. Minus 3 times 1/2 to the x plus 1. All right, so just like what we have done as far as the steps here, let's first recognize the parent function. We want to see g here as some transformations applied on the transformations. This is the information that I want to repeat. I want to emphasize that here in case I did not mention that in part A of the example. Okay, so now in our understanding, the parent function is recognized as the following one. See, let me now point your focus point into that 1/2 to the x, because as far as operation, the way how it reads here is we have to, according to PAMDAS, the order of operations, we have to handle whatever as the output of, or as the outcome of 1/2 to the x first. That's the first thing, order of operations. And then the next step is to multiply with this coefficient. So negative 3 is playing in the role of the coefficient to this function. So this function itself now is recognized as a function we now commonly know at this point, an exponential function right here. Okay, and then after multiplying with that constant coefficient, negative 3, we're going to add with that 1. So now it's clearly that the parent function is recognized as f of x equals 1/2 to the x. 1/2 to the x. And so now in that way, with what I was trying to point out earlier, then here's how my function g of x is related to f of x as a descendant right here. From whatever f of x is as the outcome, we're going to multiply the outcome of f of x with negative 3 first, and then we're going to add 1. All right, and so now once again, this is what to expect. I am to expect having some vertical scaling first. Some vertical scaling is going to happen first. And then in the next step, I am expecting to have some vertical shift, okay, due to that plus 1 like that. All right, and so now at this point, we're going to get right over. Let's quickly have a quick glance at the graph of the 1/2 to the x, right here, the parent function, to decide for ourselves the guiding points. And then we're going to take those guiding points to the other board space right there. All right, and then we're going to use them. We're going to use them for making our transformation. All right, so this is the graph of our function 1/2 to the x. All right, 1/2 to the x. And these are the plotted points right here. So we also had an example earlier in this lecture where we plotted this graph. We sketched this graph with paper and pencil right here. Okay, so these are the guiding points, and we really only need 3 points as the guiding points, but for good amount of details, let's choose 5 points. So we have these 5 points right here. Okay, and they shouldn't, at this point, once we have already seen example 1, we shouldn't be surprised about these 5 points that came out right from our table of values earlier. Okay. All right, so now I'm going to use those guiding points. I'm going to bring those guiding points that we've seen on the graph to the table of transformations here. So now one column is for the original, for the guiding points on the parent function. So I had 1 point is at, from the very left, I have 1 point at -2, 4. I had another point at -1, 2. I had another point at 0, 1. I had 1 point at 1, 1/2. And I had 1 point at 2, 1/4. All right, that should be good enough for us. And so now in the next step, again, vertical scaling must come first. So in that way, I'm going to look at the column to see how the changes will affect on the y values here by doing -3 times f of x. So I'm going to multiply -3 to every y value. Nothing will be done to the x values. Okay, so now the first pair of value becomes -2, -12. Multiply the -3, that coefficient, to every y value. Okay, and so now -1, -6, 0, -3, 1, -3/2. Okay, and then 2, -3/4. That's how my values are. That's how I multiply -3 to all the y values here, to every y value. And then now the last step is ready for me to kick in. Okay. So now I'm looking at the last one here is -3 times f of x. The final transformation is to add 1 to every y value, adding 1 to every y value. So the first pair of value becomes -2, nothing was done with the x, -11. The next point becomes -1, -5. The next point becomes 0, -2, because I'm adding 1 to every y value. Okay, and then the next point here is a 1, -1/2. I mean -1/2. -1/2 because -3/2 plus 1 like that. Okay, and then now we have 2, okay, and then this is a positive 1/4. All right, so these are the final transform points right there. Okay, so now I'm going to put these points, these final plotted points, the final guiding points on the graph right there. All right, so now this is the graph of the original parent function, 1/2 to the x. These are now the graph of this is now the guiding points. Okay, these are the guiding points of the of our function g of x. Okay, so before I put in the graph, let me get back to the board and explain a couple of things. Our coefficient in front of the function here was a negative coefficient. So that vertical scaling, aside from scaling it, aside from making it even either bigger or smaller, aside from scaling, it also caused this coefficient, because it had a negative. So it also caused the graph to flip upside down. And that's how you already saw that a little bit through the guiding points right there. Okay. So now the guiding points here form into a path that expectedly showing the bent curve here being upside down. Okay, so now here's the actual graph. All right, so the actual graph is here. So the shape is completely, the shape here is the mirror image of the beginning shape. That's the number one thing. I mean, it's not exactly the mirror image because it already has some scaling applied on top. But as far as the shape, it's reflected through the x-axis first. And then now the horizontal asymptote is now moved up. It's now shifted up to 1 unit. Okay, because we added 1 to the function. Okay, so that explains how I saw the transformation plus 1 in the function like that. Okay, and so now with this function, yes, this original parent function is just the basic or simple a to the x. So this one here has horizontal asymptote at, it has HA at y equals 0. That was the one for this. But now for this particular g of x function, then g of x, this is what we noticed right here, has one horizontal asymptote, HA, right, at y equals positive 1. All right, and then this y equals positive 1 is consistent with that value right there. Y equals positive 1 is consistent with that value. Or in other words, the horizontal asymptote is always consistent with that final coefficient that we're looking at, that final constant term that we're looking at, added to our exponential function. Okay,